Hi everyone, happy to be here with you guys at ESA Phiweek. I'm Camillo, I'm founder of Emerif, and we will be presenting today the teams that are working behind the AI4Earth challenge. Just that you know, this recording or this presentation will be recorded. If you agree with that, then everything good. Should you not, please just give a short statement about that. So, to just get started, AI4Earth. Basically, it's a 2-month challenge, an AI for Good program with over 52 participants from 18 nations that join together to highlight our impact on Earth using machine learning and Earth observation data. The final objective is to create a video with the results of each team to drive awareness about our positive and negative impact that we have on our planet. It is spearheaded by Space Hub Networks and in collaboration with us in Emerif, the European Space Agency and Fruit Punch AI. With us here today is Florian. He represents Space Hub Networks. And he will give you guys a very short introduction about their project and what they're aiming to do. So, changing screen. Florian, please.
Hello, I hope you can hear me well. My name is Florian Lippok. I would like to give you a really short introduction about Space Hub's network. That is the European funded project that is hosting this AI for Space, AI for Earth challenge. And yeah, please, next slide. What do we do within our pool of mentors? We provide business support, technical support, and funding support to pre-incubation startups and entrepreneurs, pre-acceleration startups, and post-acceleration scale-ups and SMEs, all within the context of space applications. Next slide. We also do the promotion of space downstream application, and in this respect and in this pillar, we organize hackathons or challenges and space network events. And one of these hackathons is this AI4Earth challenge. Next one. Who are we? We are partners in 6 different European countries. That is Ireland, France, Austria, Poland, Lithuania, and Romania. And the last slide. If you want to find out more about our project, please visit Space Hub's networks, and we're waiting for you. That was just a really quick introduction. I think the most interesting stuff is still to come. Thank you, Camillo.
Thank you, Florian. So, yeah, why are we here today? I think we all sense what is at stake. It's this small little marble that hosts the only life that we know. As of today, there is no other home, not for us and not for any other form of living being. We are stuck here and we better protect our home. But we are running an incredibly dangerous experiment. Burning fossil fuels, destroying natural habitats and taking more than Earth can support. And all this with only little sense about what truly is happening and what is going to happen in the future as well. So just let's recap what happened in the past year. In 2020 and 2021, we broke all storm records, 31 tropical cyclones, 14 hurricanes, 7 major hurricanes of class 3, with a total damage of 51 billion in the US alone. And fires in California burning over 4 million acres and more than 10,000 homes. The smoke created truly underlines this magnitude. And we had severe floodings in China, one of the worst in history, and near biblical locust plagues in more than 10 countries. To give you a small number here as well, swarms of 80 million in population per square kilometer were counted, and these consume food equivalent to that eaten by 35,000 people a day. And we have all heard about the major bushfires in Australia. Here again, the plumes visible from space. And since a few years, repeating fires in permafrost regions in Siberia. And this is a completely new phenomenon that possibly will even further leverage climate change. To also give you some charts, global temperature is rising a lot. In Siberia, as before mentioned, the average temperature has already reached plus 5 degrees Celsius, which you can see on the top right corner. Just to put this into perspective, the global average temperature during the last ice age, around 15,000 years ago, was minus 5 to minus 6 degrees Celsius. So not so far off the variance that we have today, but obviously in the opposite direction. And as humans, obviously, we always need to put a dollar sign to understand the true magnitudes, right? So in 2020, it was the year that has the most expensive natural disasters ever. In total, more than $20 billion disasters happened in the US alone. And out of these disasters, severe storms and tropical cyclones were the main cause. And to provide hopefully a full stop to the argument, the cause of climate change, the biggest report yet on our impact on Earth was created by the IPCC. In total, 234 direct authors from 66 countries reviewed over 40,000 climate papers with one distinctive outcome. Humans are responsible for climate change. So this is basically why we are here. To use our knowledge and capabilities to try to repay somehow nature our debt. And sometimes you have to take a step back to see really the full picture. And Earth observation can provide us a holistic view to get this full picture. But I think it's not just technology that we need in this case, but really awareness. And sometimes images tell more than 1,000 words. The final objective of AI4Earth is to create an awareness video based on Earth observation data to highlight our impact we have on our planet, positive and negative. And I have to admit, I'm extremely excited about this challenge, especially because the engagement of all teams have been extraordinary. We are sort of in the midst of this 2-month challenge. And yeah, without further ado, I would really like to give the words to the teams. We will be having 4 in total presenting today. The first is marine intelligence, remote control reef monitoring. Then we move to dying rivers and the damming race, to remote ground level pollution monitoring, and we will finalize with illegal deforestation detector in the Amazon region. So yeah, let's welcome the first team by Akanksha. The stage is yours.
Thank you so much.
Yes, we can see the slides. Okay, can you hear me well?
Yes.
Okay, thanks, Camilo, for the introduction. So yes, our group focused on marine life, specifically on remote sensing for coral reefs. As you can see in the next slide, our team is composed of 5 members. I'm Julian. Akanksha will continue the presentation later, and then there is also Jayesh, Mari, and Alessio. We have diverse backgrounds. Some of us are still studying, some are working, but we all have passion for sustainability and AI. So, okay, corals. In the next slide, you can see a few pictures of corals. We all know what corals are, at least at a basic level, but maybe some of you don't know how unique they are and what a vital role they play, not only in marine ecosystems, but in human society. Coral reefs act as a natural barrier against floods and erosion. They support 30% of all marine life. They are an important source of food and new medicines. Directly or indirectly, they provide lots of jobs for local communities. And it is estimated that about 1 billion people depend on them for food, income, or protection. Losing them would be devastating, not only from a biodiversity perspective, obviously, but also from an economic point of view. And they are dying. Maybe some of you have come across one of these news titles. You can see them in the next slide. But they are dying at alarming rates. The Great Barrier Reef in Australia has lost half of its corals since 1995. And if current trends continue, 90% of all the corals in the world might be gone by 2050 or so. And what's the reason for this? Well, surprise, surprise, climate change. mainly in the form of an increased sea surface temperature and ocean acidification. But there are some other anthropogenic causes like pollution, urban growth, or overfishing and the imbalance that creates in the marine ecosystem. Now, when corals are about to die, they go through a process called bleaching that you can see in the next slide. This bleaching process make them turn white, and it is reversible. And there is lots of very interesting research going into that process. But this whole bleaching process can happen in a couple of weeks, in a matter of weeks. So that's why it is so important to keep a close eye on them in order to be able to prevent this from happening. And for that, we have remote sensing. Specifically, the Sentinel-2 satellite from the Copernicus mission is very, very suitable because of its multispectral capabilities. So our goal is to put our grain of sand by combining remote sensing with AI techniques in order to improve coral reef monitoring. But Akanksha will tell you all about that.
Thank you, Julian. Now that we understand what are corals and why they're important, let's talk about the different steps that we carried out in our project lifecycle to produce some coral reef monitoring results. So first step was to collect and analyze different data sets and identify the regions of interest. Our second step was to build a regression model to predict average bleaching in those regions of interest. Further, we built a supervised classifier to detect specific coral regions in the satellite images by Sentinel-2. And finally, we visualized any changes in the bleaching from both numerical and image data sets, and we summarized the results and present it here for you. So here we can see that we have two data sets, the GRF data set and the Sentinel-2 satellite images, which were available via Copernicus. Overall, this gives us an overview of the project where we share the different data sets, the models, and our results. Here in the models, we analyzed correlations among different parameters, predicted bleaching, and detected coral reef regions. And in the results, we can see that we identified these positive correlations between bleaching, wind speed, and temperature. We predicted average bleaching with high confidence, that was low mean square errors, and a high accuracy in our classifier, which was greater than 90%. So this is a good overview of our data sets. We had the numeric data set, the GRF data set, and the Copernicus Sentinel-2 image data set. The spatial and the time resolution for these two data sets were different. For the GRF data set, we had multiple countries which were specifically known for having coral reefs, and the time duration was from 1982 to 2017. However, there was irregular collection of data in terms of time resolution, and that is one of the issues we discuss later in the slides as well. For the Sentinel-2 image data set, as Julian mentioned, it's really good because of its multispectral capabilities. Its location is pretty much worldwide. You just need to add the latitude and the longitude. And the time duration is from 2015 to 2021. However, the revisit time of a particular site is once every 5 days. And we access this via Google Earth Engine specifically for our task. So one of our first results include correlation analysis over all the regions that were mentioned in the GRF dataset. Here you can see on the right-hand side that the average bleaching has a positive correlation with wind speed, as well as the temperature in that region. This also is sufficient and a good proof of evidence as opposed to what was mentioned in the literature. So this is a good finding that all of the numerical information in the data sets is coherent and concise and good enough to generate nice results. So here you can see we mapped different bleaching levels and severity from 1982 to 2017. You will be able to see these red dots and their severity levels in different regions. Here you can see there are some dense regions in around Mexico, and Australia, which is the Great Barrier Reef, in Taiwan. And because of this visualization, we decided that we'll study 4 regions of interest, which are Mexico, Belize, Taiwan, and Australia. This is the focus of our study. So let's talk about average bleaching in these 4 regions. We'll first talk about Australia. Here on the x-axis, we have time, and on the y-axis, we have average bleaching. we see an upward trend in Australia, and we see that the bleaching is definitely overgrowing. And this is actually coherent with the results that Julian mentioned in the first slide, that the Great Barrier Reef has lost half of its coral reefs, right? And for Belize, there's actually a positive result that it's actually decreasing with time. So from in 2006, the bleaching levels were way higher, and it's decreasing year by year. For Mexico and Taiwan, because of the irregular data collection, we could not plot these. Otherwise, it would be an unfair comparison. But Taiwan also seemed to show an upward trend in bleaching. As shown in literature, average bleaching is directly correlated with sea surface temperature anomalies. So when we plot the graphs of average bleaching in Australia and sea surface temperature anomalies in Australia as well, we see this upward trend in both these graphs. We can see similar trends and similar graphs in other locations as well, but for simplicity, we've just added Australia here. Like we said that we built a regression model to build average bleaching, to predict average bleaching. So what we did was we divided the data set into training and test data sets. And then we predicted bleaching based on the different numerical parameters that we had. And you can see, except for a few outliers here in Australia, which is on the left-hand side, and here in Belize on the right-hand side, the model is able to predict bleaching to a good extent, kind of overlaps on most of the bleaching records, and this is shown by the mean square error of 0.01 in Australia and 0.02 in Belize. And for the same reason, we did not build a regression model for Taiwan and Mexico. However, there are other data sets we're still exploring to see if we can do that. This is from GRF, but there's another from NOAA, and we're still exploring into that direction. So these are this is the region of Belize, and this is supervised coral detection using the algorithm random forest. So one of the important things is to mention the latitude and the longitude. So we specifically chose the region of Belize because we had access to labels of 3 different types of objects, which are coral objects, which are pink in color, sand objects, which are yellow in color, and seagrass, which is mentioned in green here. And the time duration for this analysis was from January 2020 to August 2020. And then the way we split the data set into training and test was based on region. So when you're usually testing your algorithms, you're supposed to test it on unseen data. So we divided Belize into 2 different regions and tested it. And we found that it returned a pretty good accuracy of 90.95% over the Belize region. And this was really good, and this could be actually extended to other regions as well. However, we would need more domain expertise to evaluate whether those detections were actually true or not, because we do not have access to labels in those areas. We only had access to Belize in this case. So as we mentioned, we would also visualize the changes of our models. So on the left-hand side, you can see that's a region of Belize from January 2020 to August 2020 aggregated into one image. And you can see the whiteness here, which Julian mentioned is coral bleaching. On the right-hand side, you see the same region, but that's an aggregated image of January 2021 to August 2021. And you see the whiteness has actually decreased, which is a positive sign. So as Camilo mentioned in the beginning, AI4Earth challenge has both positive and negative results. So this is a positive result showcasing the Belize has actually decreased its coral bleaching in one of its coasts. So that's a positive sign for us. So as we went through our pipeline, we had a couple of challenges. I'm just going to summarize some of them. So in the data sets, there were so many diverse data sets, it was hard to aggregate them and difficult to kind of aggregate them for multi-parameter studies. So if you want to study different parameters from different studies or combine different images from different sources, the spatial resolution, the time resolution is quite different, so that's challenging. There's also lack of standardized methods for, let's say, atmospheric correction in satellite images. So this kind of results in unfair comparisons because different studies report different results, and then it actually results in the research not being very reproducible or accessible. And for machine learning, like I mentioned in the previous slides, there was lack of labeled data. Additionally, the Google Earth engine that we use does not have the capability to build complex deep neural networks, such as those which are state-of-the-art image segmentation models, which kind of limited our capabilities of supervised learning machine algorithms. Additionally, we did not explore too much of the unsupervised methods at this moment because it requires access to domain experts for verifying those results. So yeah, a solution could be to build a library with all these pre-existing atmospheric correction methods, which are already mentioned in literature, and again, pre-built and pre-trained image segmentation models, which are already present in literature. Additionally, because this field is still new, having open benchmarks and standardized data sets to increase machine learning tasks in Earth monitoring would also benefit the community. Talking about open source, we've also open sourced our code on GitHub. It's called Marine Intelligence. You can have a look at it. The link is on the slide. And the slides are also publicly available. If you just want to click on them, just go to this link and you'll be able to access them. We'd also like to thank all the collaborators, or all the organizers, and all the people who helped us through this project. Space Up Next Network for actually leading this AI4Earth challenge. Punch AI and ML Reef for providing the master classes, and ESA for providing the data sets, and everybody in our team who worked really hard to build this presentation. Thank you for your time. Please let us know if you have any questions.
Thank you very much. Perfect presentation, really excited. I would say we move directly to the next team, which is Dying Rivers and the Damming Race, presented by Kamal.
Hello, everybody. So I'm Kamal Said. Let me share my screen. Okay, so can you all see my screen?
Yes.
Okay, so I will just go ahead. So thank you all for having us today. I'll be presenting on behalf of our team. Our team is dealing with the issue of dying rivers, how climate change and the damming race are affecting our rivers and their ecosystems. So just a moment to present our team. We come from a very diverse background. We have Ingrid Hagen, a PhD student at the University of Rijeka and teaching assistant at University of Pola in Croatia. We have Tim Ufer, a Bachelor's of Artificial Intelligence from Germany. We also have Surab Kumar Barak, double degrees, actually bachelor's with honors from Kolkata, West Bengal, and currently also a second degree student at University of Calcutta, India. We have also Harsh Shukla, an ArcGIS analyst from India, and myself, Kamal Said. I have a master's in data science from Tilburg University in the Netherlands, where I live currently. So our team is very diverse, but we share a common cause that is about the most valuable resource on our planet, and that is fresh water. So what's all this about? What's the problem? Why we are even here? So first of all, a report came out a few years ago from the Worldwide Fund for Nature, outlining the risks that confront our rivers due to the damming race. There has been an expansion in dams, and this left quite a footprint on our ecosystem. They tried to compile a list of the most rivers that are facing risk from damming, and the top three are the Yangtze River in China, where there are 46 dams, and these are only large dams. So we are talking about dams that are greater than 60 meters. We're not counting large dams and other minor projects. We have also La Plata River in South America, 27 large dams, and the Tigris and Euphrates, which has 26 dams on this basin. So if we take a look here about some studies that were done on the Euphrates, for example, where it originates in Turkey, and we have a very ambitious, large-scale project called the GAP project going on the Euphrates. And we can see here in the yellow and the red regions the number of dams that choke the river from where it originates until it just and exits the borders of Turkey into Syria and downstream to Iraq. We can also see the Mekong River here, which flows through China and depends on Myanmar, Thailand, Laos, a very diverse ecosystem and a large number of countries. And we can see here in the Changsane station, upstream, we have 9 dams ahead of this station, and with 2 more actually currently being planned. So this is a very interesting area to study and see how exactly all these dams are affecting our rivers and our ecosystem. Now, I want to say that this study is not a causal study. We're not seeking to build a causal relationship between dams and whatever is happening in our rivers, but we are investigating. We're using our models to analyze imagery to tell us the story of a certain region. The story on the ground is kind of bizarre and troubling, and this is freshwater, where this is the river Euphrates. Well, we have at least 12 million people who are affected, impacted directly by what's happening in the river basin. And this is a recent photo from the ground from Getty Images to just see what's going on. So we'd like to investigate this situation. And hence our task. We would like to show the impact of large dams on river basins as they evolve through time. And one candidate that we should be looking at is the river stream flow, aka the discharge rate. That is the volume of water that flow through a given river section per second. We also will look at normalized water index, which describes the what's going on in the water body as a whole. And actually, we're going to look also at the vegetation index. So we're going to tell us something about the agricultural land, the vegetation that is around a river in its basin, how it evolves through time, how the agriculture and wetlands are affected. And we're going to look at urbanization index and see how the livelihood of people, how the urban areas are responding or affecting whatever going on in the river basin. First, we're going to perhaps show you what the river index is and what it tells us. This is a satellite imagery obtained of a certain region along the Euphrates, and it tells us what is in the bright color, what is happening to the river body itself. So we can obtain 1 image per month. We can obtain more, of course, but for our purposes, we obtain 1 image per month, and we see how each month the river is evolving, what's happening to the water index per month, and also the vegetation index. This is it isolates the agricultural lands. So we have an input. We can see with our own eyes through time how the vegetation is evolving. And also urbanization index, or the brighter areas supposed to be urban or badlands. And we can see also what's going on in the urban life within the basin. These are the indices, but what about the stream flow? Well, we could traditionally rely on measured stream flow, that on-site measurements, which is fine. In developed countries, these tend to be consistent and cover a long period of time. However, this is not the case around the world. In developed countries, we are facing major record gaps. Like I'm talking about the absence of decades of measurements. Okay, so what how we are gonna deal with this situation? The stream flow is the single most important measurements or that concerns the river. It's the amount of water that is flowing through it, and we want to address this in our project. So we would like to fill the gaps. So in our project, we're going to follow a data-driven method to fill in the gaps in the discharge records from remote sensing. So we have certain gaps, we develop a model, and it fills us with these gaps, an estimation, of course, a prediction, an estimation of what would these gaps be. And all in all, our high-end solution of the issue is we rely on satellite imagery. We get them through a processing pipeline to obtain informative feature maps. A feature map, for example, that is describe the surface water extent. That is basically a mask that isolates the mean water body from whatever surrounds it. And a map that describes the river width. Then we grab whatever available out there in the world regarding discharge or consistent on-site measurement of discharge or stream flow rates. Whatever is available, we're going to use them as labels to train our model. Then hopefully our model will tell us about the portion of the labels, the discharge measurements that is missing. And this is our overall solution. Now, this is a solution. These are the outcomes that we're trying to achieve. What about the data? So let's say this is, well, I have a certain region of interest. This is the Mekong River, the Chang Sain station along it, and this is our region of interest, for example. So we're gonna now go to Sentinel Hub. We want to obtain a historic record of imagery from the past to present to describe the story of this region. Well, the region has 9 dams, so let's see what's going on. So we go back as far as 1982 and grab imagery from Sentinel Hub, Landsat 4 and 5 to cover from 1982 to 2013. And we can go to Landsat to fill in the period from 2013 to 15, and from 16 on, we actually could, or the end of 15, we can actually now rely on Sentinel-2 imagery, which is robust, high resolution, very informative optical satellite imagery. This way, we can build a time flow, right? We can go tell a story through multiple decades of how a river region is evolving before damming, before and after damming, before climate change intensified and after climate change intensified. And here, from this region, we can grab an image per month since 1983 until 2021. One image per month through all these decades to tell us what's going on. Well, as far as our feature maps, of course, we're not going to process the raw imagery or color maps. We seek to get informative feature from them. And our features that are going to inform our model are the surface water extent masks, which describe exactly the water body. So here, for example, it should be Chang Sain, and this is the region, or the body of the river around it, and how it evolves through time, month by month. And correspondingly, for the same region, we have now a river width map that describes the width of the river also as it evolves month by month, season by season, year by year, decade by decade. And now we have useful information. We have the elements of a story to tell to the people that are concerned, that are affected by these regions. We have a water index, and a vegetation index, and an urbanization index, all through the past decades. And also through we have the stream flow record the amount of the volume of water as it is obtained by our model. These are directly can be obtained from the satellite imagery via processing, but well, the insight measurements wherever they're available, plus our model prediction are going to provide us the record of the stream flow. And this will complete the elements of our story. Now, as Camilo mentioned, we try to touch on the people to relay the message, to show to be, people aware of the impact, and we seek to produce a video to tell the story. So a video that shows 5 different time lapses, each time lapse with a different time of data, since 1984 of a given region until 2021. A color map, that's the color map of the region, and a map that describes the stream flow. And this is where our model contributes to fill in the missing gaps in this data. And a map to describe the water index, the vegetation index, and urbanization index, all a sequence of imagery, time-lapsing. You can see and feel through the image how it is evolving through time. And this is what we're currently working at when we're trying to, the message that we're trying to give. So that's it from us, and thanks to everybody, to European Space Hub, MLReef, Punch, ESA, everybody who is helping us. And that's my time, and if you have any questions.
Thank you very much, Kamal. A nice presentation. By the way, if any of the spectators have any questions, please use the chat. I'm pretty sure the teams are very eager to answer any question that you will have. We are sort of now in the mid of everything. And the next presentation is due now by Robert and Enno, and it's about remote ground level pollution monitoring. The stage is yours.
Yes, thank you, Camilo. Just gonna wait a bit for Robert. Okay, welcome to our small presentation from the air quality group. Next slide, please. So our team consists of Hannah Miles, she's a statistical analyst for a humanitarian NGO, and Robert van Dijk, he's a master's student in mechanical engineering, and myself, Enno Thiemann, I'm a systems engineer for an aerospace and technology corporation. Next slide, please. Thanks. So, our problem, the air pollution, as we all know, is a public health problem. Regarding the WHO, ambient air pollution accounts for nearly 4.2 million deaths per year due to stroke, heart diseases, lung cancer, stuff like this. Regarding the air quality, there are a lot of different molecules or different stuff in the air which contains the information for the air quality. So there are a lot of summation of different stuff. For example, the air quality also contributes to global warming through emissions, for example, from NO2 or also CO2. For the example on the right, you see a picture of Sao Paulo from 2019. This picture is during the day, also it doesn't look like this. That's because the air is so polluted from a wildfire, which is pretty close. Next slide, please. So our main goal is to predict the NO2 concentration on surface level with satellite data. We take NO2 because that's an indicator for emission, and also therefore if there are humans in this area, and for example in cities there's a lot higher NO2 resolution. And the NO2 the concentration is also an indicator for CO2 emissions. On the picture on the right, you see the green dots. That's all ground station air quality monitoring data. So for example, in Europe, also the US, there are a bunch of air quality measuring data. But for example, in Africa or South America, there are very few. So the people could need some techniques to measure their air quality. And our approach is based on Sentinel-2 and Sentinel-5P data. And we want to take in supervised learning and use the surface level monitoring ground station data as the ground truth for the supervised learning. Yeah, we want to predict the air quality for the areas in Africa, also South America. We found a quite recent paper, estimation of air pollution with remote sensing data, which is like our guidance for this project. Next slide, please. Okay, regarding the data acquisition, we downloaded some data of surface monitoring stations from an open air quality organization, which contributes and provides open access air quality data sets around the globe. All these monitoring stations are measuring NO2 we just took, and we also took the coordinates of the same station, so we can take a buffer around this small point. So we have an area of interest where we download the images from Sentinel-2 and Sentinel-5P. Regarding Sentinel-2, we downloaded for this area of interest all the bands which are provided. They're about 60 to 10 meter resolution. And we take the Sentinel-2 data because it gives a good idea of the landscape, if it's the city in the area of interest, or forest, or some sea, stuff like this. And we take the Sentinel-5P because Sentinel-5P is quite recent satellite which measures a lot of air quality molecules, for example, ozone, methane, formaldehyde, but also nitro oxide. But Sentinel-5P just takes like the column of the atmosphere, so you can just look at the atmosphere and determine the NO2 concentration in that. So that can still differ quite a lot from the surface level NO2 concentration. And the Sentinel-5P has a lot of different resolution, as you can see. It's very, very high resolution. But yeah, we still have had to manage to get this all together. Next slide, please. Okay, regarding the pre-processing, after we downloaded all our data, we had to do some data refinement for the monitoring data because there were a lot of outliners or invalid measurements that we had to filter, but also we just took the monitoring stations which monitor data every day. So that's also limiting the data set. But still, around the world, there are a lot of data, which is also helpful for low cost sensors. They are very helpful for this data. So in the left here, you can see a small area of interest from Sentinel-2 picture. That's an RGB picture from Cape Town. And in the middle, pretty much, there's the ground station, air quality measuring station for our ground truth. And at the bottom, you see Sentinel-5P data. On the right, there's just no data at all. That's what we also had to handle, because the NO2 value from Sentinel-5P is not measured directly. It's a level 2 product, and therefore it needs to be calculated. And if there are any clouds or stuff like this above the area of interest, the NO2 value can't be calculated. And regarding the high resolution, as I just said before, we did some B-cubic interpolation to have the Sentinel-2 and the Sentinel-5 data on the same resolution of 10 meters per pixel. Yeah, and this pre-processed data can then be fed into our model, and I will give over to Robert.
Oh, I bet I just went all the way through the slides. All right, so the model that we're going to use is based on the one that's used in the paper that Enno mentioned before. It's just that we use that as a baseline, and then we try to improve from there as well. See what parts of the model could be improved or what inputs could be improved. So what it basically consists of is a two-part model. It uses a ResNet 50, which is pre-trained on some satellite data set already. And it uses a separate convolutional neural network, which then these outputs are combined to make the eventual prediction of NO2 in the data. So all 12 bands go into the ResNet, and only one band basically of the Sentinel-5P data goes into the convolutional neural network. And these values of Sentinel-5P are all mean for either a month, a week, or a year based on what resolution we're looking at. We'd like to see if we can make predictions based on daily assumptions, on daily data or weekly data. That will be most relevant. So some preliminary results. We're still into getting the model to work as accurately as possible. So these results aren't too great yet. But in the end, what we want to do is look at, for example, Africa, then look at a larger area and take some of the Sentinel-2 and Sentinel-5 samples from there, from smaller patches, pre-process those and feed those to the model. And then eventually those two samples would then give a prediction for that square of 1 by 1 by 1 kilometer, approximately 1.2. And then eventually, if you do that well enough, then you can piece together the puzzle of the larger area of interest. Right now, the model is not doing too great yet. We need to definitely train it some more because the predictions are actually negative in some cases. So that's not even possible for of course, but we just need to fine tune it a bit with more data. We probably need to do some more pre-processing for the samples that we input to the model. So some future directions, pre-processing updates, just like I just mentioned, to make sure that the model does at least come close and stops outputting negative results. Then we want to take a look at differing the data inputs. Right now, all 12 bands are separately used as inputs for the model. That seems a bit excessive. Perhaps we can combine them already into indices, like the urbanization index or the vegetation index, to already do some of the work for the model for it before we feed the inputs to it. And we would like to see if we can perhaps predict some other Sentinel-5P particles like ozone, and or use those particles to predict some ground pollution levels as well. And then we've got some model and training architecture fixes we want to implement as well. Okay, well, that was our presentation on air quality. Thank you for your attention, and if you have any questions, we would like to see them in the chat.
Thank you very much. Nice presentation. I would say let's move to the last presentation that we have today. Last but not least, Guillaume, you will be presenting deforestation detector in the Amazon region. Have fun, enjoy.
Yes. Hi everyone. Can you all see my screen? I'll be a bit shorter than the other ones as we're not as advanced, but still deforestation is an important problem. So we thought it was important to have a word here. So thank you for welcoming us at the Phi-week. My name is Guillaume, and I have the pleasure to represent my team today and show you a bit of the work we've done so far, tackling deforestation thanks to deep learning. So just as the other teams, we're a bunch of passionates with very diverse experiences. Even though everyone's not an expert in the field, we joined the challenge to learn from each other and join forces to try and use AI for positive impact. So we have Genevieve, Ram, Seal, and Bharat, and myself, quite an international team. And we've been working on a deforestation detector. So Deforestation is a commonly known phenomena and is gaining in visibility due to its increasing rate, specifically in certain areas such as the Amazon basin. In 2020 versus 2019, for example, we were talking about a loss of 11,000 square kilometers, which corresponds to the equivalent of a third of Belgium. So meaning that since I started talking, we probably lost around 3 football pitches. Also, in the battle against climate change, avoiding deforestation is a key tool for decarbonization. It's more impactful than planting new trees and regenerating new forests, even though all efforts have to be combined. So as you see on this graph, the 23, the number of 23 is the amount of gigatons of CO2 we will have to remove or avoid in order to meet the 1.5 or 2 degrees target by 2030. And 7 of those 23 can be achieved by natural climate solutions. And inside of those natural climate solutions, half of it, as you can see, is by avoided deforestation. So it's avoidance, and then the other part is restoration. So satellite images can help us measure the impact of deforestation. We can't control what we can't measure. That is the main principle of Earth observation. So with our naked eye, we can see the difference here between these two pictures, distant from 18 years. But year-on-year changes are much more challenging to spot, and the amount of data is too high as well. So that is where AI come to play in order to process all these images. So our approach in our project has been first to perform an NDVI assessment, so assess the vegetation index, to evaluate the vegetation loss and spot potential areas of deforestation. Our focus has been on the year 2020 and 2019 in the Amazon region, as well as in some parts of Paraguay. And our data source has been the Copernicus program with the Sentinel-2 satellite. So this is, the NDVI assessment is not AI-based, it's just an introductory approach to make kind of an assessment. But our main goal is to build a convolutional neural network for change detection. And this is our main objective, as I say. And then as a third step, we would like to stack on these images a map of protected areas. All these are still work ongoing, so we don't have any results to show today, unfortunately. But I'll rather explain a little bit more each of the steps. So for the moment, we have the NDVI for all our images that we've divided into smaller slices. And you see here a visual of true color, false color, and the NDVI on the right. And then our goal with this is to compare both 2018 and 19 and compute a pixel by pixel difference in vegetation. Then the big chunk of our work is to build a performant CNN for change detection. And to help us in this task, we didn't invent or reinvent the wheel. We're trying to replicate the work of a team from the University of Brasilia. And they are working on a UNet model to do a binary classification for forest and non-forest. So for this, we're using an autoencoder, which has proven to be efficient in such a semantic segmentation task, where you need to keep the spatial architecture of your image. So it's worked like a downsampling and then upsampling of the satellite images. And finally, of course, our satellite images only would not be sufficient. We need to have the ground truth information to be able to train and evaluate our model with the actual deforested area. This is provided by the PRODES project, led by the Brazilian National Institute of Space Research. So you see here a representation of the binary classes of forest and non-forest. And then finally, if we have time, our end goal would be to map the protected areas and see if some has been impacted by vegetation change. Obviously, vegetation change isn't always deforestation. There are natural vegetation change, but we can see identify deforestation in big gaps in the NDVI. And then, yeah, one of our most direct impact probably in our project will be in the end to produce an impactful video of the human footprint on Earth that will serve an awareness campaign. So stay tuned to the EO4Earth challenge and to what comes next. That was it for me and for our team. Thank you very much for listening. Thank you to all our partners, Footprint AI, ESA, MLReef, Space Up Networks, Mothership, Brimatech. And if you have any question, do not hesitate to ask. Thank you.
Thank you, Guillaume. Yeah, thank you very much for all the presentations. Just as a reminder, who was here? These are the teams. So if you want to know more about them or something like that, please feel free to reach out. They're surely happy to provide you more information about the state, what they're doing. I, on my side, want to finalize as well with a last note on the partners. It has been a really great journey so far. We've been working together since around 1.5 months on this project already. And it has been, on my side at least, a blast. The people are extremely motivated. They're working on their free time on this project. And this is something that really needs encouragement. I think we all here believe in the purpose of this challenge to really create awareness about what we humans are doing on planet Earth. This could not be possible with you guys. I think the atmosphere in ESA is a special one to really demonstrate what can be done with technology, passion, and obviously a lot of hours. In that sense, I want to thank the partners as well, starting definitely with Space Up Networks to initiate this project. Want obviously to start the European Space Agency and all the Phiweek team that has been supporting us directly as well, and the teams. They have been doing masterclasses showing us the right direction and supporting the teams on technical issues. The people in the team behind Footprint AI, they are incredible. They are in the Netherlands and are focused on really driving their SDGs based on machine learning approaches. Yeah, and last but not least, obviously me and the MLReef team that supports and hopefully encourages more people to join this challenge. On that side, thank you very much, and hope to see you soon. Good, I think that's it. Thank you very much, everyone. Thank you for the great presentations. I think we and you guys made an incredible job.